All right, how you guys doing today? This is Mr. Muscarella coming at you, and we are going to take a look at an example to determine whether a series converges or diverges using this thing called the integral test. Now, in our first example, we've got this series from n equals 1 to infinity of n times e to the negative n. So what we're going to have to do first is we're going to let f of x equal what this series kind of looks like. And what you're going to do here for this is pretty much you're going to take this and rewrite it, and you're going to replace all the n's with x's. Pretty straightforward. Now, for the integral test, you're going to have to show three things. First thing you're going to show is that f is positive. Then you're going to have to show f is continuous. And the third thing you're going to have to show is that it's decreasing. And it's got to be decreasing for all x's greater than or equal to 1. Okay, so that's going to be one of the things we're going to have to show. Now this first derivative test, that's going to help us out with the decreasing part. Now to show f is positive, let's just kind of plug, we can take a look at that and plug in a number greater than 1, so say like 2. If we plug in 2, so say f of 2, that's going to be 2 over e squared, which we definitely know that's positive. If we plug in 3, we'll get a similar result being positive, and 4, and so on. So that is taking care of condition number 1. The second thing we have to show is that f is continuous, and the function is going to be continuous because there's no vertical asymptotes anywhere along there, because e to the x will always return a value no matter what. So our function is going to be continuous, and then the last thing we got to do is show that our function is decreasing. So in order to do that, we're going to use the first derivative test. So taking the derivative of x over e to the x is going to give us this equation here. So when we take a look at that, let me just kind of scoot this up a little bit, you'll see that we end up with 1 minus x over e to the x. Now all of this tells us that what we need to do is go ahead and find any critical values. Now we have a critical value at x equals 1, so we're going to go ahead and make a little sign chart here. Now 1 is right over here on this graph, and we'll come back here to the graph in a second. Now if I plug in a number before 1 into the first derivative, so say I plug in 0, I'm going to end up with something that is positive, because 1 minus 0 is 1, and e to the 0 is 1, so that's definitely positive. What that tells me is that my function, f of x, that's going to be increasing. Now if I go on the other side of 1 to say like 2, so if I plug in 2 to my first derivative, I get 1 minus 2 is negative 1, and then e squared is positive. So negative over positive, that gives me something that's negative, which means my function is going to be decreasing. Now this was a way of analyzing this analytically. We can also take a look at things graphically and before 1. So if I take a look just before 1, my first derivative is, and what we kind of want to analyze is before that. Notice this is always above the x-axis. Now my function itself is increasing. So those two things tie in together. So analytically we found that before 1, our function was increasing and our first derivative was positive, and then after 1 we can kind of see also that our function, so let me switch it up here to a little bit different color. So right after here our function is below the our derivative is below the x-axis, which means it is negative, so our first derivative is negative, means that our function is going to be decreasing. So those two things, so we took care of that third step now, and that was the last thing that we had to do. So you have to show those three things whenever you're using the integral test. Now, since those three conditions are met, we're going to move on and do something which looks a little bit familiar. We're going to use the limit process to help us determine whether an improper integral converges or diverges. So we're going to have the limit from 1 to infinity of x over e to the x. Of course, we're going to replace that with the infinity, we're going to replace that with a b. From there, what you're going to do after that is we're actually going to use, in order to help us figure this out, we're going to use a tabular method. And the tabular method is one technique that you can use to find integrals such as this one. So tabular method is broken up into 3 columns, so we're going to have u is one of the columns, and then dv, so the antiderivative is going to be another one. And then this column right here is just going to be plus and minus. We're going to alternate signs. So what I want to do is let x be the value of u. So then what I do next is find the derivative of x. Well, that's just 1. And the derivative of 1, of course, is 0. Now for dv, I'm going to let that be e to the negative x. So I'm just going to take this piece right here, the denominator e to the x, and I'm going to write that as e to the negative x. Now when I find its antiderivative, I'm going to have e to the negative x, but don't forget the negative out in front of that. And of course, when you take the antiderivative of negative e to the negative x, you're going to be back at e to the negative x. Now alternating signs, so it's just going to be plus, minus, and then plus. So all of that table, we're going to use that to help us kind of come up with what this would integrate to. So the table, the way it works, so you're going to go here and then down here. So you're going to find the product of those, which is just going to be negative x e to the negative x, which you can rewrite as negative x over e to the x. So that's another way you could write that. For my second term, so we're going to have negative 1 times e to the negative x, so negative e to the negative x, or you could write that as 1 over e to the x. So either way you write that is okay. So that tells me that this piece right here, oops, I made a little right-o, this should be b right here, not infinity. So we're going to have the limit as b goes to infinity of what we just found from the tabular method. So that's going to really help us out here with this piece. Once we know that, it's just a matter of taking your time and doing your substitution correctly. Now I'm going to do this the long way, just because I want to illustrate a point here, because there's going to be a little bit of a wrench thrown in here. So we're going to find the limit as b goes to infinity of all of this. Now when you substitute infinity in for b, you end up with some crazy stuff right here. Check that out. You end up with negative infinity over infinity. What? That's just craziness, because you should recognize that that is not possible. That's not good. And what happens when you have negative infinity over infinity? Well, that's an indeterminate form, which means you're going to have to invoke L'Hopital's rule. Or was it Bernoulli's? I don't know. History calls it L'Hopital's rule, so we're going to go with that. So we're going to have to use L'Hopital's rule, which means on this term right here, the negative b over e to the b, we're going to have to find the derivative of the numerator and then the derivative of the denominator. This other piece right here, these two terms right here, you can probably combine those pretty easily. Now, when you do that, you'll end up simply with 2e. Now this term right here, when you have e to the infinity right there, 1 over e to the infinity, this piece right here is going to end up giving us just 0. So that's this 0 right here. So we take the derivative of negative b over e to the b, and that gives us negative 1 over e to the b. Our second term, that's 1 over e to the infinity, that blew up and went to 0. And then our other piece was 2e. So again, we're just going to take our time, and when we plug infinity into negative 1 over e to the b, of course that goes to 0 again. So you're just going to finally end up with the answer of 2 over e for this particular integral. Now, what that tells us is that our integral does converge, that our series is going to converge by the integral test. Now you have to be careful though, because this doesn't tell you what the actual sum of the series is, because hopefully you remember your algebra days when you first learned about this little symbol right here, this sigma. That means you find the sum of a bunch of terms. So that sum of a bunch of terms, it doesn't tell us what that sum is. It just tells us that that sum does converge to some number, but it's not 2 over e. It just tells us, since the integral converges, that this series is going to converge. And why does it converge? It converges by the integral test. All right, so that's it for example number 1a. Thanks for watching, and I'll see you guys soon for example 1b.